Okay, hello and welcome to our, next in the series where we were looking at energy. Now, we started off at Key Stage 3. All that time ago there was 6 little lessons to do with Key Stage 3 energy. And then we had a following 8 lessons of energy at Key Stage 4. What we're going to look at today is conservation of energy, which we did mention at Key Stage 4, but what we're actually going to look at more in depth is the idea of work, energy and power. Now, up until now, energy, what we've been looking at has predominantly just been the production of electricity. Although we've mentioned the 10 different types of energy, we have just been focusing on how we can make use of it in terms of that electricity production. What we're going to look at today is a more sort of biological look at energy. So how much energy that we use ourselves and how much energy can be used mechanically. But we will get to that, so that will be part of work, energy and power, which will be the second part of today's lesson. First lesson, what we're going to do is have just a quick little recap about our conservation of energy. So as I said, we mentioned this at Key Stage 4, so this is the idea that no energy is lost in the system. But first of all, what is energy? Now, the proper description of energy is the capacity of a physical system to perform work. So energy itself is it's quite hard to actually fully pin down exactly what energy is. You can't call it one thing. What it actually is, it's the product of a system, but it's also the beginning of a system. So this says energy is the capacity of a physical system to perform work. So conservation of energy. What we've got is just a brief little bit of history here. We've got Mr. Galileo Galilei, famous for many different discoveries that he did make, but he was actually the first person to, or accredited to be the first person to start making comments about the conservation of energy in the system. This was way back in the 1600s, with an idea or an experiment called the interrupted pendulum. Now, I'm not going to go into the ins and outs of that. If you really are that interested, just look it up. Look up Galileo. He's a really interesting guy. But he was only the first person to mention it. The first person accredited with actually making a mathematical equation for it is this gentleman here, Gottfried Leibniz. Now this again is sort of later on in the 1600s, so he's the first person to be accredited with the actual writing of mathematical equations to try and explain the conservation of energy. So when I say the conservation of energy, what do I actually mean? Well, as in physics, as we like to do, we like to accredit letters to things that have absolutely nothing really to do with what they actually mean. So here, E equals T plus V. So what we're actually saying is that the total energy in the system is equal to the kinetic energy plus the potential energy that was originally started the system and became, through an energy transfer, leaving that system. So what this actually is saying is that the kinetic energy plus the potential energy equals the total energy. So there's no energy loss. In a lot of cases as well, the kinetic energy and the potential energy are actually the same thing. They're actually the same total. So it's literally just a case of having the two same numbers together to get our total energy. So what are our equations? So our equations for kinetic energy is half the mass of the object times its velocity squared, okay? And our gravitational potential energy, which is actually the mass times the gravity by the change. This triangle here means delta, so it means the change of height. So what you can actually do is backtrack and work out, if you know the mass of an object, and say you're going to drop it from 2 meters, so what you need to do is take the mass of that object, say that mass is 2, times it by gravity. So just for the sake of ease, we'll call gravity 10 meters per second, but it's about 9.81, but we'll call it 10 for ease. So our mass would be 2, our gravity is 10, so that's those two times together, so that's obviously 20. And then our delta height, so our change in height, which is 2 meters. So it's our mass, which is 2, our gravity is 10, and our delta in height, which is 2 as well. So that would be 2 times 10 times 2. So that would give us 40. So we know our potential energy. So therefore, if we know that our potential energy, then the kinetic energy itself would actually be the same as well. So you can backtrack and work out the rest of the equations here. So you could work out the velocity and the time it would take for that object to fall 2 meters. So what we're going to do is we're actually going to have a look a little bit more in depth into the maths involved, not just in the conservation of energy, but actually just working out how much energy you would use within a system, which is where we're going to move on to now. So energy, work, and power. So, hopefully all of you people have seen this already now. This was actually part of our lectures of Key Stage 4, drumming into most kids hate learning GCSE energy names. And of course this stands for our 10 different energy types that we learn at Key Stage 4 level. So this is obviously a good way, as I said before in our previous lessons, to try and remember all the different energy types. And again, hopefully some of you have felt my pain to begin with of trying to remember what this second E was. It took me a good couple of days to keep remembering. It was elastic potential, elastic potential. And any of you that saw that mini in the sling, you'll now know exactly why and how I remember it. So what we're going to move on to first look on is our look at work. So work, as remember, our definition of energy, which is energy is the capacity of a physical system to perform work. So that eternal question, how do we work out work? I know it's a really well structured question, but it's exactly what we want to know. How do we work out work? But at the same time that we're going to work this out, so our equation for work is the force created times by the distance of which that work is taking place. Now, our second equation under here was actually to do with a bit of trigonometry. We've got some cosine work in here. Don't worry about that too much at the moment. We'll get to that at the end. So at the moment, what we're focusing on is our work times force times the distance. So what you'll see here is our equation, which is W equals F times S. S is the standard sign for distance or for displacement. Why is S? It's because it is, because we like to do things like that. So yeah, work equals force times distance. So force, how do we work out force? Well, what we're actually going to do is go all the way to the end. We're going to work out our energy, we're going to work out our work, and we're going to work out our power as well. So power is actually the amount of work divided by the time or the duration of which that work was done. But there's actually two ways of working out power. There's that way, and the second way is, again, which is our force coming back in here. Power, which equals force, times the velocity or the speed, which is obviously in meters per second. So obviously we've got a lot of equations here we need to try and out. The main one that we obviously at the moment is trying to work out force. What is force? So let's try and we'll do this in a way that we can try and get a grasp on how much energy is in the system. So first things first, I'm sure everyone recognises this particular shot of this guy chilling out in his last 10 metres of his world record, breaking 100 metres run. Of course this is Usain Bolt. So what we've got down here at the moment is his first 30 metre split times. So he did first 10 metres in 1.85 seconds, his second 10 metres in 1.02 seconds, and his third 10 metres in just under a second, 0.91 of a second. And we know his mass as well. He texted me the other day, I asked him, he's eaten a couple of McDonald's this week, so he's actually got his mass up to 93.9 kilograms. So, with this bit of information, or just his split times and his mass, what we can actually do is take a look at how to work out not only just work, but obviously his power and his work, his power, and everything else that we want to have a look at today as well. As you can tell, I haven't opened my calculator, which is something we're going to need and something I would recommend that you have as well. So first things we're looking at, we know his mass, and we know the time for his split times, and we also know the distance for that. So we want to work out the amount of power. Now power is something that you will generally not have to look at until maybe the first year of A-level. Force and work, you will definitely need to know how to work out at Key Stage 4. Speed and acceleration at Key Stage 3, going into Key Stage 4 as well. So ultimately what we want to do is get to the point that we can work out how much work he put in and how much power he created while he was doing this. So these are all the different equations that we need. So to get to force, well, to get to power, we need to work out force times distance. To work out force, what we actually need to do is do the mass times his acceleration, but we don't know his acceleration. All we know is the set time of which he did 3 different sections of 10 metres. So to work out his acceleration, we need to work out, this is delta, again this triangle, which is the change in speed divided by the time. Now again, we don't know his speed, but we do know the distance that he was travelling and the time he took while he travelled that. So we need to work out speed. So if you can follow me, what we need to do, to work out power, we first need to work out work. To work out work, we first need to work out force. To work out force because of the acceleration, we need to work that out. And to work out acceleration because of the speed here, we need to work that out. So let's take this from the very beginning. So Usain Bolt's first 10 metres, he did in 1.85 seconds. So if we remember, speed is equal to distance, which should be an S, okay, divided by time. So in that case, what we actually have is distance, which is 10 metres, and our time, which is 1.85 seconds. Now, for those of you who are organised enough to have your calculators with you, I'm sure you're shouting at your computer to tell me exactly what the answer is. I'm a little bit slower, but what we actually have is 5.4. Now, because this is in metres and this is in seconds, our answer unit will be metres per second. Now, so that's his actual speed, that's his average speed over the 10 metres. So what we need to work out now is his acceleration. So his acceleration, if you remember, is the change in speed divided by the time taken. So his change in speed, we're assuming that this is going from 0. It's from 0 metres, so he's starting from a standstill. So therefore his change in speed is from 0 to 5.4 metres per second. So therefore the change in speed is 5.4 metres per second. Divided by the time, again this is 1.85 seconds because this is how long it took him to do it. So therefore our answer which comes out for that, which is our 5.4 metres per second divided by 1.85 gives us 2.92. Now this is acceleration. What we have here is metres per second and seconds for our 2 units. So what we actually have here is metres per second per second. Now what you'd actually write is metres per second to the power of 2. Okay, so acceleration is metres per second because it's the amount of how faster you are going over that set distance of time. Okay, so what we have now, what we need to do is work out that all-important force. So force is equal to the mass times by the acceleration. So now we know, as we said, you know, Usain Bolt texted me the other day and he told me his mass, which is in kilograms, which is 93.9 kilograms. And as we worked out, his acceleration at this particular moment in time is 2.92 metres per second squared. So therefore, our force comes out at 93.9 kilograms times by 2.92 metres per second, which comes out at 274.19. Now this is force. Force, our unit for force, although you could say is kilograms and metres squared per second, actually what it is our good old man newtons. So it actually comes out as 274.19 newtons. So now force, from here we could work out power, because we have our force and we have our velocity, we have our speed. But what we want to do, let's take it the long way, let's work out work as well. So work is equal to, if we go back here, obviously we still have all of our ones worked out here. So work, remember, is force times the distance. So work, so our force, which is 274.19 newtons, times by the distance, which again is only 10 metres. We're just looking at that initial 10 metres. So therefore it's equal, all we need to do here is obviously our decimal point, we're timesing it by 10, we just need to move it along one more. So we've got 2,741.9. Now work, because we've worked on in newtons and got Newton meters, what work actually is, because it's a type of energy that's being used, the unit for work is J. It's the joules. Joules of work done. So now we know that joules, we can now work out the amount of power that he was using. So if we take the initial one of working out power, which remember is work divided by time, what we'll do is make a little bit of space up here. So our initial, which is power, equals work divided by time. So our work is 2,741.9 joules divided by time, which again is at 1.85 seconds for the initial 10 meters. So again, if you get your calculators out, 2,741.9 divided by 1.85 gives us 1,482. Now, here is where we could have units. What we've got here is joules and we've got seconds. So joules per second. Now, the official name for joules per second is the watt. The W-A-T-T, not watt, but it's the watt. Watt stands for joules per second. So, in the first 10 meters, Usain Bolt was using 1,482 joules per second. So he was using 1,482 watts. Now what you can actually do is to change that to another unit which is called kilowatts. So that's kilo, which is Latin for 1,000. So what it would actually be is 1.48 kilowatts. And if we put that into context, 1.5 kilowatts will probably get your hairdryer working. So in his first initial 10 meters, Usain Bolt was using the same amount of power as a hairdryer. Doesn't really make it sound as much of a good feat, does it? So what we'll do, we'll take this second one now, his second 10 meters. So again, we'll start with the speed. We're going to go through this a little bit quicker now because hopefully you're with me. So speed, we've got distance divided by time. So it's 10 and it's divided by 1.02. So obviously that's not going to change our things too much, but 10 divided by 1.02, which gives us our 9.8 meters per second. So now acceleration, which is our change in speed. Now what we've got here is we're not starting from zero this time because we're looking at our second 10 meters. So what our start speed is actually that 5.4 meters per second here from our previous calculations, because Usain Bolt is already travelling, so he's already doing 5.4 meters per second, and that needs to be subtracted away from our 9.8 meters per second. So yeah, so what we'll do, I'll write that the proper way around so we don't end up with a minus figure, because obviously that will make things a little bit more confusing. So we go 9.8 meters per second, which is our speed now, minus our 5.4 meters per second, which is the speed we started with. And again, that is divided by time. And this is the time for our second 10 meters, which is 1.02 seconds. 1.02 seconds. So that would give us an acceleration. So if we work out our 9.8 minus 5.4, which gives us 4.40, so 4.40 divided by 1.02 equals 4.31 meters per second squared. So what we're going to go on to next? We're going to go on to next is we're going to look at our force. So again, it's our mass, oh, forget the right page, it's our force, so our mass again, which is 93.9 kilograms, and it's times by acceleration, which is 4.31. So anyone else with a calculator? I really wish I could hear you at the moment, it would make my life so much easier. So it's 93.9 kilograms times by the 4.31, which is equal to 404.7 newtons. Remember, our unit for force is newtons. So, work is force times by the distance. So again, what we're doing is our force, which is 404.7, times by our distance, which is still only 10 metres because we're working out in 10 metre sections. So our work is 4,047, and it's work, so it's energy, so therefore it's joules. So 4,047 joules is how much energy that Usain Bolt used in that second 10 metres. So how much power did he produce? So his power, if we do it the first way round, which is work divided by time. So therefore we have 4,047 joules divided by 1.02 seconds, which is equal to 4,047 divided by 1.02 is equal to 3,967, and it's power, so it's joules per second, which is the watt. So let's work it the other way around. As we said, there's two ways of working power. So the other way of working out power, which is force times by the distance, if I can remember. So it's force times the distance. So our force, which is 4,047 times by the distance, which is 10. Oh, I got that wrong. So our force actually is completely wrong. Our force is actually 404.7 times by 10, which actually gives us 4,047 watts. So as you can see, the two different ways of working out power do give you slightly different answers. This first way, the work divided by time, is the general way of working out power. The second way, force times distance, is not quite as accurate. It's recognised as not quite as accurate as it is for power. So at this point, we can see that actually Usain Bolt is at his peak here. He's used 3,900 odd watts of power. So he's actually using now twice as much, actually over twice as much power that he was using the first time round, where we had 1,400. So 2 times that would have been 3,000. He's using nearly 4,000 now. So at this point, with his last 10 metres, he's actually chilling out. He's no longer actually running or expelling as much energy as he was before. As you can see, he's not actually expelling anywhere near as much energy as he was before. And in fact, I can tell you that that second 10 metres was actually his peak of power used. And why is this? Well, the fact is it takes a lot more energy to get up to a top speed than it does to maintain that top speed. Because you have to take over the initial force of going from 0 to your maximum speed. Once you're at that top speed, the only things you're fighting are wind resistance and things like that. So you're actually, there's a lot less power, a lot less work to actually maintain your top speed once you're actually there. So the amount of power that he actually used, let's try and put that into context. Now those of you who enjoy fast cars, this is a Bugatti Veyron. So a Bugatti Veyron can actually go from 0 to 60 in 2.65 seconds. 2.65 seconds, and its mass is actually 1,888 kilograms. So what we're going to do is we're going to do exactly the same as we've just done for Usain Bolt, but we're going to work out how much energy is involved in the Bugatti Veyron going from 0 to 60. Now the first initial problem that we have here is that we need to work out speed. Now speed is in meters per second, but the speed that we've been given is in miles per hour. Okay, so we need to convert that into meters per second. So in 1 mile, there is roughly 1,606 meters. Okay, and in 1 hour, there is 3,600 seconds. So if you take those two numbers and you divide them by each other, what you actually get, if I can remember from when I did this before, is roughly about 0.45. You get 0.446, so we'll call it for ease, we'll call it 0.45. So what you can actually do now is you can take your 60 miles an hour And if you then times it, by this 0.45, you will get the number 27. So what have we done here? We've got 60 miles an hour, which is our change in speed, and we're timesing it by 0.45, which is our ratio of meters and seconds to the ratio of miles and hours. So what we actually get here is 27 meters per second. So 60 miles an hour is exactly the same as travelling 27 meters per second. So how does that help us? Well, our first one is speed equals distance divided by time. So if we get our equation triangle, yeah, so we have our speed equals distance over time. So I'm sure you all recognise this triangle here. So what we actually want to work out to start with is the distance, because the distance is going to be useful. How much time or how much distance did it take for this vagabond to go from 0 to 60? So we need to resort our equation out here. We know the speed and we know the time, because the time is 2.65 seconds and we've worked out the speed, which is 27 meters per second. So what do we want to work out? We want to work out distance. So if we cover our distance, that means it's actually distance is equal to speed multiplied by time. So what we do is our distance, which is equal to our speed, which is 27 meters per second, times by our time, which is 2.65 seconds. And what that actually gives you is 71.55 meters. So actually, you say in 3/4 of the distance that Usain Bolt did his world record attempt, the vagabond is already doing well over 60 miles an hour. So what we'll do is we'll take our acceleration now. So our acceleration, which remember is the change in speed over time. So our change in speed is 27 meters per second, and our time is still 2.65. So that is 27 divided by 2.65, which gives us 10.19 meters per second per second. So again, force now. Force, we're going to look at the mass times by the acceleration. So our mass we know to be 1,888 kilograms. And our acceleration we now know to be 10.19 meters per second squared. So exactly what's the force does that give us? So it's 1,888 times by 10.19 gives us 19,238, and that's force, so that's newtons. So I'm going to have to give myself a little bit more space up here now. So what we're going to do now is work out work, and then we're going to work out power. So work, remember, is force times by the distance. Now this is where it became important that we worked out distance first. So our force is 19,238 newtons times by our distance, which we know to be 71.55 meters. We worked that out from the very beginning. So that's our 19,238 times by 71.55 meters gives us 1,376,478. And now this is work, so this is energy, so this is joules. That's the amount of joules of energy used by the vagabond to get from 0 to 60. So then let's work out power. And we'll just do the first way of working out power, the more accurate way of working out power, which is our work divided by the time taken. So therefore that is 1,376,478 joules divided by the time, which is 2.65 seconds, which then means that we get 1,376,478 478 divided by 2.65 gives us 519,425 watts of power. So that's a lot of power. That's a lot of power used by that car to get from 0 to 60. Okay? So I hope that this has helped with all of the maths that are involved in working out work and working out power. As I said, work you may well come across at higher tier key stage 4. Power you'll really only generally come across at A level. So what's the last thing that we were talking about that said at the very beginning was work at an angle. So how does this affect? Now, one thing you must remember with work at an angle is that the force must be at a different angle to the object. So originally my thought, and I'm sure it's a misconception that you may well have, is that if you're running up a hill, it's going to take more energy. Well, yes, it is going to take more energy, but in the ways of working out work at an angle, it actually is not, because the force is still travelling at the same distance. Let me try and explain this in a way that I'm actually not confusing myself as well as confusing you. So what I'd actually want to do is say this is my hill, okay, and I've got Usain Bolt running up this hill. So this is my really poor version of Usain Bolt running. So what is actually happening here is that he is putting force to go forward. So therefore the work he's doing is also to go forward at the same angle. So actually this is not work at an angle because all the forces are still in the same direction. What we had in our original picture, which is a box trying to be moved this way, but with a force that's going this way at an angle to the direction of which we're actually moving it. So this is what we had here, which is our 30-degree angle. So as we go back here, then we have our work, which is our force times by our distance. Now luckily enough for you, my diagrams come up with my force already, okay? So if we go back to here, it's our force times by our distance. So if we take our force, which is 100 newtons, and we're going to try and move this 5 meters. So it's a little bit simpler compared to the rest of the maths that we've been doing so far today. So say this is 15 kilograms, our force is 100 newtons, and we're trying to move it 5 meters. So therefore work is force times by the distance, and in this case, because it's work at an angle, so work, oh, that is some horrendous writing by me, I do apologise. Work at an angle is force times distance times by the cosine of the angle. This is where our trigonometry is coming in. So what we need to do is I need to open this up into a scientific calculator. So our normal force times distance would literally just be our 100 newtons of force times by the 5 meter distance that we want to take it. So our first force here, our first one here, so number 1 would be our force of 100 newtons times by the distance of 5 meters, which would then give us 500. So that is work. Okay, so that's again energy, so that's 500 joules. Now work and angle will be 100 newtons, which is our force, our 5 meters, which is our distance, but also our cosine of the angle, and our angle at this time is 30 degrees. So what we need to do is if we do 100 times by our 5 meters times by our cosine 30. Oh, I should have done this before. So what we actually need to do is 100 times by 5, which obviously gives us 500, times by 30 cosine gives you 433 joules. So what that's actually saying is that with work at an angle, generally speaking, the angle is actually at 30 degrees in this example, then it actually takes less work, less energy input to move the same object the same distance. Okay, so that is work at an angle. Now, I have done a lot of talking in probably what is not as short a space of time that I originally hoped it to be. I hope this has helped to clear up your concepts of work, energy and power at Key Stage 4 going on to A level, and also conservation of energy. That is the last in the series of our look at energy. Thank you.